Space is full of amazing things that are hard to believe. There's a planet where it rains glass at 5,400 miles per hour, and another one made of diamond. Black holes can slow down time, and some stars are so heavy that just a teaspoon of them would weigh as much as a mountain. Galaxies are moving away from each other faster than light, and what we see is only a small part of the universe. Now let's explore some of the most incredible facts and discover the strangest things out there. In the vast expanse of space, there exist worlds so alien and extraordinary that they defy our understanding of what planets can be. Among these, a unique and fascinating type of planet has captured the attention of astronomers: diamond planets. These exoplanets, which are planets outside our solar system, are thought to be incredibly rich in carbon. Under immense pressure and heat, this carbon could form vast diamond landscapes, transforming these planets into something almost unimaginable. One of the most famous candidates for this is 55 Cancri e, a super-Earth located about 40 light-years away in the constellation Cancer. A super-Earth is a type of planet larger than Earth, but smaller than the gas giants like Neptune or Jupiter. What makes 55 Cancri e stand out is its composition. Unlike Earth, which has a core rich in iron and silicates, 55 Cancri e might have an interior dominated by carbon. Due to the extreme pressures and temperatures present on this planet, much of this carbon could exist in the form of diamonds. Diamonds form on Earth through a process that requires high pressure and temperature, deep within the Earth's mantle. The conditions on planets like 55 Cancri e far surpass those found on Earth, leading scientists to hypothesize that diamonds could form on a massive scale there. The planet orbits its star so closely that a year on 55 Cancri e lasts only 18 hours. Temperatures on its surface can soar to over 2,400 degrees Celsius, 4,352 degrees Fahrenheit, creating an environment where carbon could crystallize into diamond deep below the surface. The sheer scale of diamond formation on a planet like 55 Cancri e is difficult to imagine. On Earth, diamonds are rare and highly sought after. But on a planet with such a rich carbon composition, entire mountain ranges or vast subterranean layers could be made almost entirely of diamond. This would make 55 Cancri e and planets like it unlike anything we've ever encountered in our solar system. The idea of a planet covered in diamonds also challenges our notions of value and rarity. While diamonds on Earth are precious and rare, existing in small quantities, the abundance of diamond on these planets would make it a common material there. The natural forces at play on 55 Cancri e create an environment where the very thing we value so highly on Earth would be abundant and possibly even mundane. In addition to 55 Cancri e, other carbon-rich exoplanets could exist across the galaxy. These planets, orbiting stars with the right composition, would form in regions rich in carbon, producing similar conditions that could lead to diamond-rich worlds. The discovery of such planets is not just a curiosity, it expands our understanding of the diversity of planets that can form in the universe. Earth-like planets, with their silicate and iron cores, might be just one type among countless others that include carbon-based planets like these diamond worlds. The study of diamond planets is still in its early stages, as detecting the composition of distant exoplanets remains a challenge for astronomers. Current technology, like the use of spectroscopy, allows scientists to analyze the light coming from these planets to infer their composition. In the future, more advanced telescopes may be able to directly observe these planets, confirming their internal makeup and possibly providing a glimpse of their dazzling surfaces. The potential discovery of planets with enormous diamond reserves is a reminder that the universe holds many surprises. What we consider rare and valuable on Earth might be common on other planets, and worlds like 55 Cancri e push the boundaries of our understanding of planetary formation. These diamond planets, with their extraordinary conditions, demonstrate the sheer variety and strangeness that exists beyond our solar system. Space is often referred to as a vacuum, but the term can be misleading. Contrary to common belief, space is not a perfect void. In fact, even in the most distant and seemingly empty regions of the universe, there are particles, though they are incredibly few and far between. These particles, usually atoms of hydrogen, helium, and tiny traces of heavier elements, make up what is known as the interstellar medium. The interstellar medium, although extremely sparse, is present everywhere in space. On average, there may be only one atom per cubic centimeter in the vast emptiness between stars. To put that in perspective, a cubic centimeter of air on Earth contains trillions of molecules, so space is still almost completely empty compared to Earth. But this minute amount of matter, spread across the universe, has profound implications for how space functions on a larger scale. The particles in the interstellar medium do not just float idly. They are part of a thin plasma, particles that have been ionized, meaning they carry an electrical charge. This plasma plays a vital role in space phenomena. For one, it acts as a medium for the propagation of electromagnetic waves, such as light and radio signals. Without these particles, the transmission of information across the cosmos would be fundamentally different. One of the most significant roles of the interstellar medium is in the formation of galaxies. Over vast periods of time, gravity pulls together these sparse particles, forming clouds of gas. These clouds eventually collapse under their own gravitational pull to form stars and subsequently galaxies. Therefore, without the interstellar medium, the universe would not be able to evolve as it has. Stars, planets, and galaxies might not have formed at all. Moreover, the interstellar medium influences the distribution and behavior of cosmic radiation. Cosmic rays, which are high-energy particles traveling through space at nearly the speed of light, interact with the particles in the interstellar medium. This interaction can alter their course and energy. As a result, the interstellar medium plays a protective role for celestial bodies, including our solar system, by helping to diffuse and scatter these high-energy particles. Though the density of particles in the interstellar medium is extremely low, the cumulative mass across the universe is significant. When considered over vast areas of space, the mass of these sparse particles contributes to the overall dynamics of the universe. This is particularly important in understanding the large-scale structure of the cosmos and how gravity affects it. The existence of this medium means space behaves more like a diffuse ocean than a complete vacuum. In summary, space is not an absolute void. It contains a thin yet essential presence of particles that form the interstellar medium. These particles, though few and far between, are fundamental to the formation of stars, galaxies, and even the propagation of radiation across the universe. The cosmic microwave background, or CMB, is a subtle yet essential clue that reaches us from the dawn of time itself. This faint glow, detectable across the sky in all directions, is a relic from the universe's earliest moments, offering scientists a unique glimpse into its infancy. Approximately 13.8 billion years ago, our universe began with an event we call the Big Bang, a massive expansion from an incredibly hot and dense state. In those first moments, the universe was filled with an intense opaque plasma of particles, primarily protons and electrons, scattering light constantly. During this time, photons, light particles, couldn't travel far before being deflected by other particles, meaning the universe was essentially a glowing, opaque fog. But around 380,000 years after the Big Bang, something remarkable happened. The universe cooled enough for protons and electrons to combine into neutral hydrogen atoms, allowing light to travel freely. This marked the point of recombination, a turning point when the universe shifted from an opaque plasma to a transparent state, allowing the photons from that time to travel vast distances. These very photons have journeyed across the cosmos for billions of years, spreading outward as the universe expanded. They eventually reached Earth as the cosmic microwave background radiation we detect today. The CMB isn't visible to the naked eye, but with specialized radio telescopes, scientists can observe this faint microwave glow permeating the entire sky. It's almost uniform in temperature at around 2.7 Kelvin, just above absolute zero, with minute fluctuations of about 1 part in 100,000. These tiny variations hold critical information, acting as a snapshot of the early universe's density and temperature differences, revealing a landscape of slight imperfections in an otherwise smooth, homogeneous cosmos. These imperfections are thought to be the seeds of the galaxies and clusters of galaxies that would eventually form over billions of years under the influence of gravity. By meticulously studying the CMB, scientists have unraveled crucial insights about the structure and composition of the universe. They've found evidence that the universe is mostly made up of dark energy and dark matter, mysterious components that don't emit light but shape the cosmos through gravitational forces. Through observations of the CMB, scientists also confirmed that the universe is flat on a cosmic scale and that its expansion rate aligns with predictions made by general relativity and inflationary cosmology. Inflation, a rapid expansion that occurred fractions of a second after the Big Bang, explains why the CMB appears nearly uniform across vast distances, as this early growth smoothed out any larger initial irregularities. The CMB is like a fossil, a preserved trace from a time long past, showing us not only how the universe began, but also hinting at its eventual fate. The continued expansion observed in the universe today, influenced by dark energy, suggests it will keep expanding, growing colder and more dilute over trillions of years. This path, traced back to its roots in the CMB, provides a powerful narrative about our cosmos' birth, evolution, and destiny. In sum, the cosmic microwave background isn't just a glow from the past, it's a fundamental piece of evidence about where we came from, how the universe developed, and how it may continue to evolve far into the future. Its faint, nearly uniform presence serves as a cosmic time capsule, forever linking us to the universe's origins and allowing us to unlock the secrets of the cosmos. Time dilation and gravity is one of the most fascinating concepts in modern physics. The idea that time itself can bend and shift depending on where you are in the universe challenges our everyday understanding of how time works. Most of us are used to thinking of time as a constant, a universal clock that ticks away evenly no matter where we are. But the reality is far stranger. Time does not pass at the same rate everywhere. It can be stretched or compressed by the influence of gravity. This concept, known as gravitational time dilation, is a direct consequence of Einstein's theory of general relativity. The theory tells us that massive objects like planets, stars, and black holes actually bend the fabric of space-time around them. This bending creates a kind of well in space-time, and the closer you are to a massive object, the deeper into the well you go. Time, as it turns out, is affected by this warping of space-time. The deeper into a gravitational well you are, the slower time moves relative to someone further away from the massive object. One clear example of this phenomenon is found right here on Earth. The difference is minuscule, but clocks that are located at sea level, where gravity is slightly stronger, tick more slowly compared to clocks on top of a mountain, where gravity is weaker. This has been confirmed through incredibly precise atomic clocks. While the difference in time is only a fraction of a second over many years, it demonstrates how gravity can slow the passage of time. Now imagine this effect magnified. When you move closer to something much more massive than Earth, such as a black hole, time dilation becomes far more pronounced. Black holes, with their incredible density, warp space-time to an extreme degree. Near the event horizon, the boundary beyond which not even light can escape, the pull of gravity is so intense that time appears to come to a standstill for an outside observer. If you were to watch an object, say a spacecraft, approach the event horizon of a black hole, something extraordinary would happen. As the spacecraft got closer and closer, you would see it begin to slow down. Its movements would become increasingly sluggish. As it neared the event horizon, the spacecraft would appear to almost freeze in time. From your perspective, the closer it got to the black hole, the slower time would pass for the spacecraft and its occupants. In fact, you would never actually see the spacecraft cross the event horizon. It would just seem to hang there, frozen in time. However, for those on the spacecraft, things would feel very different. From their perspective, time would be flowing normally, just as it does for us here on Earth. But the universe outside the black hole would appear to speed up. They would see the stars whirling past, galaxies evolving, and the universe aging rapidly, all in the span of what felt like normal time for them. This difference in the passage of time is what makes gravitational time dilation such a strange and mind-bending phenomenon. Gravitational time dilation has been observed and measured in real-world situations, such as in experiments involving satellites orbiting the Earth. GPS satellites, which orbit high above the Earth, experience time slightly differently than we do on the ground. Without accounting for this difference, GPS systems would be completely inaccurate. The satellite's onboard clocks tick slightly faster than those on Earth because they are farther from the planet's gravitational pull. Scientists must take this time dilation into account to ensure that the positioning data we rely on is correct. The extreme version of time dilation near black holes remains largely theoretical, as we have not sent spacecraft close enough to a black hole to observe it firsthand. But the math and physics behind it are solid. These predictions are based on Einstein's equations, and so far, all experimental evidence has confirmed them. What makes this phenomenon even more intriguing is the possibility that, under the right conditions, time could be manipulated. If we could find a way to harness the effects of time dilation, space travelers, for instance, could experience time at a different rate than those on Earth. This could open up possibilities for interstellar travel, where astronauts might journey to distant stars and return to find that much more time had passed on Earth than for them. This concept, often explored in science fiction, is rooted in the real physics of time dilation. In summary, gravitational time dilation reveals that time is not an absolute fixed entity. It can stretch and slow down under the influence of gravity. The closer you are to a massive object, the slower time passes for you. This has been observed near Earth and confirmed through precise measurements. But near even more massive objects, like black holes, this effect becomes dramatically more pronounced. The idea that time can essentially freeze near a black hole is one of the most mind-bending implications of general relativity and challenges everything we think we know about the flow of time in the universe. Rogue planets are among the most mysterious and fascinating objects in our universe. Unlike planets that orbit stars, these solitary worlds wander through space with no fixed home. They are known as rogue because they've been ejected from their original solar systems, likely due to violent gravitational interactions with other massive objects, such as larger planets or nearby stars. These interactions force them out of their orbits, and they become drifters, unbound and alone in the vastness of the cosmos. The discovery of rogue planets challenges our understanding of how planets form and evolve. Traditional planetary formation models describe planets developing within protoplanetary disks around young stars. Over time, these planets settle into stable orbits, held in place by the gravitational pull of their parent star. However, rogue planets defy this model. The fact that they exist, impossibly in enormous numbers, indicates that the early stages of planetary systems are much more chaotic and violent than previously thought. It also suggests that planet formation isn't always a stable process, but rather one that can lead to dramatic outcomes, including planetary ejection. Without a star to orbit, rogue planets exist in perpetual darkness, making them some of the coldest objects in space. They receive no warmth from a host sun, and their temperatures can plummet to extremes. While Earth and other planets in our solar system rely on the sun's energy for heat and light, rogue planets must sustain themselves without any external source. They likely possess frozen atmospheres and icy surfaces, or if they are gas giants, they may have thick, cold, gaseous layers. Despite the cold, some scientists theorize that certain rogue planets could still have the potential for internal heat. This heat might come from radioactive decay or leftover heat from their formation, which could create subsurface oceans beneath thick layers of ice. However, this remains speculative, as detecting and studying such hidden features is extremely challenging given their distance and lack of illumination. Astronomers have only recently confirmed the existence of rogue planets, and the methods used to detect them are still evolving. Since these planets don't emit light and don't orbit stars that would make them visible against the backdrop of space, they are incredibly difficult to spot. Researchers rely on a technique called gravitational microlensing to detect them. This method observes how a rogue planet's gravity bends the light from a distant star when it passes in front of it, creating a temporary brightening effect. These brief moments are key to identifying these elusive objects. The development of this technique has opened a new window into understanding just how many rogue planets might exist. Some estimates suggest there could be billions of these wandering worlds within our galaxy alone, a number that exceeds the total known stars. The presence of such a vast number of rogue planets suggests that planetary ejection might be a common outcome in the evolution of many star systems. This challenges long-standing views about the stability of planets and suggests that our solar system's stability might be more unusual than previously thought. It also raises intriguing questions about the potential for life. Without a star, rogue planets would seem inhospitable, But if any possess enough internal heat and liquid water beneath their surfaces, they might host life in forms we have yet to imagine. The study of rogue planets is still in its early stages, but as technology advances, astronomers are hopeful that they'll be able to learn more about these mysterious objects. Future missions and telescopes designed specifically to detect these faint dark worlds will help to reveal the true nature and origin of rogue planets. What's already clear is that they are not rare anomalies, but rather a common and integral part of our galaxy's structure. Understanding them will not only reshape our understanding of how planetary systems form and evolve, but also expand our view of what a planet can be. Quasars, short for quasi-stellar radio sources, are among the universe's most fascinating and powerful phenomena. These cosmic objects are powered by supermassive black holes located at the centers of distant galaxies. Despite being over billions of light years away, quasars are so incredibly bright that we can observe them from Earth. In fact, they outshine entire galaxies, radiating energy equivalent to that of trillions of suns. Their extreme luminosity makes them some of the brightest objects known to humanity. The immense energy of a quasar is produced by the black hole's accretion disk, the swirling mass of gas, dust, and other material that spirals into the black hole. As this matter accelerates toward the event horizon, the gravitational forces cause it to heat up to millions of degrees. This intense heat generates massive amounts of electromagnetic radiation across the spectrum, from visible light to X-rays and even gamma rays. The radiation produced by quasars can travel for billions of years across space, allowing astronomers to detect these objects even from vast distances. A key reason why quasars are so bright lies in the process of accretion. As material falls toward the black hole, it doesn't simply disappear into oblivion. Instead, before being consumed, the material forms a disk around the black hole. The gravitational energy of this infalling matter is converted into radiation due to the friction and collisions within the disk. The closer the material gets to the black hole, the faster it moves, generating even more energy. Some of this energy is released in the form of intense jets of particles shooting out at nearly the speed of light. These jets can extend for thousands of light years, further contributing to a quasar's spectacular brightness. The study of quasars provides valuable insights into the early universe. Because the light from the most distant quasars takes billions of years to reach us, observing them is like looking back in time to the universe's early stages. Many quasars formed during the peak period of galaxy formation, helping astronomers understand how galaxies and their central black holes evolved over cosmic time. By analyzing the light emitted by quasars, scientists can study the distribution of matter in the early universe and learn more about the conditions that existed just a few billion years after the Big Bang. Quasars also help us probe the behavior of black holes. Supermassive black holes, with masses millions to billions of times greater than our Sun, are at the heart of these objects. The growth of these black holes is closely linked to the development of the galaxies that surround them. When a quasar is active, it signifies that the black hole is in a feeding phase, devouring large quantities of material and emitting enormous amounts of energy. This process can have significant effects on the surrounding galaxy, as the powerful radiation and jets from the quasar can influence star formation and the distribution of gas within the galaxy. One of the most interesting aspects of quasars is their variability. Unlike stars, which shine relatively steadily, quasars can flicker and change brightness over short periods of time. This variability is thought to be caused by changes in the rate at which material falls into the black hole, as well as instabilities within the accretion disk. By monitoring these changes in brightness, astronomers can learn more about the processes occurring near the event horizon of the black hole. Despite their incredible brightness, quasars are relatively small in size. The central region of a quasar, where the energy is produced, is typically no larger than our solar system. Yet because of the immense amount of energy they emit, quasars can outshine entire galaxies that span hundreds of thousands of light years across. This makes them excellent beacons for studying the distant universe. Gamma-ray bursts, GRBs, are the most powerful and energetic events ever observed in the universe. These extraordinary explosions release immense amounts of energy, far surpassing anything we experience on Earth. In just a few seconds, A single GRB can release more energy than our sun will emit over the entire span of its 10 billion year lifetime. This makes them not only awe-inspiring, but also critical to understanding extreme cosmic events. GRBs occur through two main processes. The first involves the collapse of a massive star, far larger than our sun, at the end of its life. When such a star exhausts its nuclear fuel, it can no longer counteract the inward pull of gravity. As the core collapses, it forms a black hole or neutron star. During this collapse, jets of particles are ejected at nearly the speed of light from the star's poles, creating an intense gamma-ray emission, what we identify as a gamma-ray burst. The second type of GRB occurs from the violent merger of two neutron stars. These collisions also result in the formation of a black hole, with similar jets of gamma rays shooting outward. Gamma ray bursts are divided into two categories, short and long. Short GRBs, lasting less than 2 seconds, are usually linked to the collision of compact objects like neutron stars. Long GRBs, which can last from a few seconds to several minutes, are generally associated with collapsing stars. Both types are rare, and when they do occur, they emit their energy in focused beams, rather than in all directions. This makes them extremely bright, but also means that only a small portion of the universe will ever see them. The energy in a GRB is so intense that, if one were to occur within a few light years of Earth, it could strip away the ozone layer that protects life from harmful ultraviolet radiation. Without this protective layer, the increased exposure to ultraviolet rays could trigger a chain reaction of biological harm, potentially leading to mass extinction. Fortunately, GRBs tend to occur in distant regions of the universe, often billions of light years away from us. Their origins are typically in young, star-forming galaxies where massive stars are more common. Scientists study GRBs using a combination of satellites and ground-based observatories. Instruments like the Fermi Gamma Ray Space Telescope and the Swift Observatory are specifically designed to detect these bursts and determine their origin and intensity. Because GRBs travel at the speed of light, by the time their signals reach Earth, the explosion itself has already happened long ago. Observing them provides a glimpse into the distant past, revealing the conditions of the early universe and the processes driving its evolution. These bursts are also critical to our understanding of cosmic elements. The violent nature of GRBs plays a role in the creation and distribution of heavier elements, such as gold and platinum, throughout the universe. The neutron star collisions responsible for short GRBs produce these elements, which eventually become part of planets, stars, and other celestial bodies. In addition to their destructive potential, GRBs offer a valuable opportunity for scientists to study black holes and neutron stars. These extreme environments push the laws of physics to their limits, helping researchers explore concepts like general relativity and quantum mechanics in ways that are impossible to replicate on Earth. Despite the inherent danger they pose, the likelihood of a GRB affecting Earth remains extremely low. Astronomers monitor the sky continuously to catalog these events and ensure early detection, though the vast distances at which they occur provide us with a natural safety buffer. Space is already an incredibly cold place, but there exists a location that holds the record as the coldest known spot in the entire universe, the Boomerang Nebula. Situated about 5,000 light-years away from Earth in the constellation Centaurus, this extraordinary nebula has captured the attention of scientists due to its staggering temperature, which plunges to just 1 degree above absolute zero, 1 Kelvin. This is colder than the average temperature of space itself, which hovers at around 2.7 Kelvin due to the cosmic microwave background radiation. The Boomerang Nebula stands as an astonishing outlier, making it a critical subject of study in understanding the physics of the universe. The central feature of the Boomerang Nebula is a dying star, similar to our Sun, which is shedding its outer layers. As stars approach the final stages of their life cycle, they often eject vast amounts of gas and dust into space, creating a planetary nebula. In the case of the Boomerang Nebula, the gas is being expelled at an incredibly high rate, faster than in most other similar systems. This rapid expansion causes the gas to cool dramatically as it spreads outward. The process can be compared to how air cools when it escapes from a punctured tire. The faster the gas expands, the colder it becomes. The gas in the Boomerang Nebula is expanding at about 500,000 kilometers per hour, which is an extraordinary velocity, contributing directly to its super-chilled state. What makes the Boomerang Nebula even more remarkable is that its temperature is lower than that of the cosmic microwave background. The cosmic microwave background, CMB, is the residual thermal radiation from the Big Bang, and its uniform temperature of 2.7 Kelvin sets a kind of baseline for coldness in space. Yet the Boomerang Nebula, due to its unique conditions, manages to undercut even this fundamental temperature, making it the coldest known place in the universe. This extremely low temperature is a result of the nebula's complex interaction between the star at its center and the surrounding gas. As the star sheds its outer layers, the expanding gas not only cools, but also forms a bipolar structure, meaning the material is ejected in opposite directions, giving the nebula its distinct bow tie or boomerang shape when observed through telescopes. This unusual shape has helped astronomers identify and study the phenomenon in more detail. The Boomerang Nebula's frigid conditions offer more than just a record-setting temperature. It serves as a natural laboratory for studying the processes that govern the life and death of stars. Observing this nebula helps scientists understand how stars evolve and die, particularly those that are similar in size and composition to our Sun. When stars like our Sun run out of nuclear fuel, they eventually expel their outer layers into space, leaving behind a hot core that becomes a white dwarf. The gas and dust expelled during this process often create beautiful nebulae. But in the case of the Boomerang Nebula, the sheer speed of the gas expansion leads to this extreme cooling effect. Moreover, the Boomerang Nebula's extremely low temperature challenges scientists to rethink certain aspects of astrophysics. The laws of thermodynamics, as applied on cosmic scales, behave differently under such extreme conditions. The near absolute zero temperature of the Boomerang Nebula pushes the boundaries of what is possible in terms of cooling in space, providing invaluable data for scientists studying low-temperature physics and cosmic evolution. The study of the Boomerang Nebula also has implications for our understanding of the universe's past and future. By analyzing objects like this nebula, astronomers can trace the changes in temperature and density that occur during a star's death. Dark matter and dark energy are two of the most mysterious and profound concepts in modern cosmology, reshaping our understanding of the universe. Together, they account for the vast majority of the universe's content, yet both remain largely unseen and poorly understood. Starting with dark matter, this substance is thought to make up approximately 85% of the universe's total mass. Dark matter does not emit, absorb, or reflect any electromagnetic radiation, which is why it cannot be observed directly. Despite this, we know dark matter exists because of its gravitational effects on the galaxies and galaxy clusters we can see. The universe behaves as if there is more matter than we can detect. For instance, stars and galaxies orbit much faster than they should if only the visible matter were present. These observations have led scientists to conclude that there must be a hidden component, dark matter, contributing significantly to the total mass. One of the key roles of dark matter is its influence on the formation and structure of the universe. In the early universe, right after the Big Bang, dark matter played a crucial part in helping galaxies form by acting as the scaffold around which visible matter could clump together. Without dark matter, the universe as we know it, with its galaxies, stars, and planets, may never have come into existence. It essentially acts as the invisible glue holding the universe together. Despite these important functions, the true nature of dark matter remains elusive. It could be composed of yet undiscovered particles that interact with ordinary matter only through gravity. Numerous experiments are being conducted to detect these particles, but so far none have been successful. Its elusive nature continues to challenge physicists and astronomers, making dark matter one of the greatest unsolved puzzles in science. Even more mysterious than dark matter is dark energy. While dark matter exerts gravitational forces, pulling matter together, dark energy works in opposition. It is a force driving the accelerated expansion of the universe. In 1998, observations of distant supernovae revealed that the universe's expansion is speeding up, not slowing down, as previously thought. This was an unexpected and groundbreaking discovery. Dark energy is thought to make up around 70% of the universe, Unlike dark matter, which clusters around galaxies, dark energy is believed to be evenly distributed throughout the universe. Its presence can be inferred from the accelerating rate at which galaxies are moving away from each other, indicating that some unknown force is counteracting the pull of gravity on large cosmic scales. The precise nature of dark energy remains one of the biggest questions in cosmology. One hypothesis is that dark energy is related to the vacuum energy described by quantum mechanics, the energy inherent in empty space. Another possibility is that dark energy may be a new kind of field or force that we have yet to fully understand. Whatever it is, dark energy plays a crucial role in the fate of the universe, possibly dictating whether the cosmos will continue expanding forever or reach some unknown end state. Together, dark matter and dark energy dominate the universe, making up about 95% of its total content. Despite their prevalence, we have only scratched the surface in understanding them. The ordinary matter that we can observe directly, stars, planets, galaxies, constitutes just a tiny fraction of the universe. The rest remains in the shadows, influencing everything but revealing itself only indirectly. Our current understanding of the universe is thus incomplete, and much remains to be uncovered about the invisible forces shaping the cosmos. Neutron stars are among the most extreme and fascinating objects in the universe. They are the remnants of massive stars that have undergone supernova explosions. After a star exhausts its nuclear fuel, its core collapses under the force of gravity. If the core is massive enough, but not large enough to become a black hole, it forms a neutron star. These stars are incredibly compact, squeezing a mass greater than that of our Sun into a sphere no more than about 20 kilometers in diameter. To put this into perspective, the density of a neutron star is so extreme that a single teaspoon of its material would weigh around 6 billion tons on Earth. The reason neutron stars are so dense lies in their structure. They are composed almost entirely of neutrons, subatomic particles with no electric charge. When the star's core collapses, protons and electrons are crushed together under immense pressure, combining to form neutrons. This process leaves behind a dense ball of neutrons packed so tightly that even atomic structure is destroyed. The material within a neutron star is at such extreme densities that the ordinary forces we experience on Earth no longer apply. In addition to their immense density, neutron stars have other remarkable properties. They possess incredibly strong magnetic fields, trillions of times stronger than Earth's magnetic field. These magnetic fields can accelerate particles to nearly the speed of light, creating powerful jets of radiation. Some neutron stars, known as pulsars, emit beams of electromagnetic radiation from their magnetic poles. As the neutron star rotates, these beams sweep across the sky. If Earth happens to be in the path of these beams, we observe a regular pulse of radiation, like a cosmic lighthouse. The rotational speed of a neutron star is equally astounding. While a newly formed neutron star may rotate dozens of times per second, some, known as millisecond pulsars, can spin hundreds of times per second. This rapid rotation is due to the conservation of angular momentum. When a massive star collapses into a much smaller neutron star, it retains its angular momentum, causing the neutron star to spin at extraordinary speeds. Pulsars, the neutron stars that emit regular beams of radiation, have provided invaluable insights into the nature of space and time. The regularity of their pulses allows astronomers to use them as precise cosmic clocks, testing the effects of extreme gravity and helping to confirm Einstein's theory of general relativity. Pulsars have also been used to detect gravitational waves, ripples in space-time caused by the acceleration of massive objects. One of the most interesting phenomena involving neutron stars is the formation of binary systems, where two neutron stars orbit each other. Over time, these stars lose energy through gravitational wave emission, slowly spiraling toward each other until they eventually collide. These neutron star mergers produce incredibly energetic events, releasing bursts of gravitational waves and electromagnetic radiation. Observing such events has provided astronomers with a new way of studying the universe and has helped them better understand the behavior of matter under the most extreme conditions. Neutron stars are not only important for understanding the life cycles of stars, but they also offer a unique laboratory for studying fundamental physics. The conditions inside a neutron star are unlike anything we can recreate on Earth. The extreme densities and pressures within neutron stars allow scientists to study how matter behaves when subjected to these intense forces. Understanding the interior of neutron stars could provide answers to some of the most profound questions in physics, such as the nature of neutron-rich matter and the limits of atomic structure. The universe is vast beyond our comprehension. What we call the observable universe is just the portion we can see or measure, spanning roughly 93 billion light-years in diameter. This might seem enormous, but it's important to understand that it's only a small fraction of the entire universe. The observable universe is limited by the speed of light in the time since the Big Bang, about 13.8 billion years ago. Light from distant galaxies takes time to reach us, and this defines the edge of what we can observe. Anything farther away simply hasn't had time to send light that could reach us, so it remains beyond our detection. But the universe doesn't stop at this boundary. In fact, it likely extends far beyond what we can observe, possibly infinitely. The reason we can't see beyond the observable universe is not because space ends there, but because the universe has been expanding since the Big Bang. This expansion creates a horizon beyond which light from distant objects can never reach us. Some regions of space are receding from us faster than the speed of light due to this expansion, making them forever inaccessible to our telescopes and instruments. This leads to the idea that the observable universe is like a tiny island in a much larger ocean. We are bound to the light we can detect, but there is an overwhelming amount of space beyond that we will never be able to explore. The universe may contain regions with different physical laws, unknown forms of matter, or phenomena we can't even begin to imagine. Yet we have no way of observing these distant realms, because the light from them will never reach us. The reason for this lies in the nature of space itself. Space is not static, it's constantly expanding. This expansion can occur at different rates depending on the distance between objects. At very large distances, galaxies and other cosmic objects are moving away from us faster than the speed of light, which is allowed by the rules of general relativity. This doesn't mean that the objects are traveling through space faster than light. It's the space between us that's expanding, carrying those objects away from us. As a result, the size of the observable universe is increasing over time, but there will always be a limit to what we can see. The regions that are receding faster than the speed of light are effectively lost to us forever. No matter how advanced our technology becomes, no new light will ever reach us from beyond the observable universe. This vastness presents one of the greatest challenges in cosmology. We can only study what we can observe, meaning our understanding of the universe is inherently limited. Beyond the observable universe could lie regions of space that are completely different from what we know. There could be different distributions of galaxies, clusters, or even other forms of matter and energy that we have no way of detecting. The idea that the observable universe is just a small part of the whole also raises questions about the overall structure of the universe. Is it infinite? Does it curve back on itself? Scientists are still exploring these questions. And while we have mathematical models that predict certain behaviors of space on large scales, they remain unproven due to the limits of what we can observe. In simple terms, the observable universe represents the limits of what we can know with our current tools and understanding. It serves as a reminder of how little we have explored and how much is still beyond our reach. We are confined to this small part of the cosmos, unable to look beyond the horizon of light that defines our observable limits. The concept of the multiverse challenges everything we know about the nature of reality. According to some scientific theories, the universe we live in is not the only one. Instead, it is just one of countless universes that exist side by side in what is known as the multiverse. These parallel universes could differ from ours in fundamental ways. Some could be nearly identical to ours with only minor differences, while others might operate under completely different laws of physics, making them entirely unrecognizable. The idea of a multiverse is rooted in theoretical physics and cosmology. Some interpretations of quantum mechanics, particularly the many worlds interpretation, suggest that every decision or random quantum event creates a branching of universes. In this view, whenever a quantum event occurs, the universe splits into multiple versions, with each new version corresponding to a different outcome. This means that for every possible outcome of every event, whether it's flipping a coin, the result of a cosmic explosion, or a person's decision, there is a universe where that outcome is realized. If true, this would imply the existence of an infinite number of realities, each following a different path. Another line of support for the multiverse comes from cosmology. According to the theory of cosmic inflation, the universe expanded rapidly after the Big Bang, stretching space at an incredible rate. This inflationary model of the universe leads to the possibility that what we consider the universe is just one bubble in a vast sea of other bubble-like universes. These other universes could be incredibly far away from ours, so far that we may never be able to interact with or observe them directly. Each of these universes might have emerged with its own unique set of physical laws and conditions. The multiverse theory also offers a potential explanation for one of the most puzzling aspects of our universe, the fine-tuning of the fundamental constants of nature. In our universe, certain physical constants, such as the strength of gravity and the speed of light, are set at very specific values that allow life to exist. If these constants were even slightly different, stars might not form, chemical reactions necessary for life might not occur, and planets capable of supporting life might not exist. The multiverse theory suggests that if an infinite number of universes exist, each with different physical laws and constants, it's not surprising that at least one of these universes, ours, has the right conditions for life. Despite its appeal, the multiverse remains a highly speculative concept. Currently, there is no direct observational evidence for the existence of other universes. The idea of parallel universes is supported by mathematical models and theories, but proving their existence would require a level of technological and scientific advancement that we have not yet achieved. In fact, some scientists argue that the multiverse is beyond the realm of testable science and therefore lies outside the bounds of what we can definitively know. However, the implications of the multiverse theory are profound. If the multiverse exists, it would fundamentally alter our understanding of reality. Every possible outcome of every event would exist somewhere, meaning that there could be countless versions of you, living in universes where you made different choices or experienced different circumstances. It also suggests that our universe is not unique, but just one of an infinite number of realities. This vast expanse of possible realities raises philosophical questions as well. What does it mean to be real if there are infinite versions of reality? Does every possible version of history in the future exist somewhere, playing out in parallel? These are questions that stretch the limits of human understanding and challenge the way we think about the universe and our place within it.